Hi everyone, my name is Jesse Angeles and today I want to present you a research about adaptive evolution in totalistic cellular automata. In here we explore the evolution of one-dimensional cellular automata, starting from a single active cell looking for the largest evolution that neither tends toward infinite nor die out immediately. At this point, I know most people here know what a cellular automata is. However, for those who are not familiar, it's a regular grid where each cell updates value based on interactions with its neighborhood. And also, there are totalistic cellular automaton, where the rule depends only on the sum of the values in the neighborhood. If we start from a single active cell, a subset of rules creates finite lifeforms. What is this? The evolution takes a finite number of steps until vanishing, like in these examples. This finite lifeforms is characterized by emerge from a single active cell, evolve through space and time, and eventually fade until all cells become inactive. Some rules produce very short lifeforms that disappears immediately, and others create infinite growth, expanding forever. But in between those extremes, there are rules that produce fascinating dynamics. And also, these finite lifeforms can be found in the totalistic cellular automaton space. One of the most fundamental problems in this field is the huge number of possible rules. The number of totalistic rules increase exponentially when we add more states or increase the radius of the neighborhood. This exponential growing makes the brute force search exploration extremely expensive because we can't evaluate all the rules quickly. It becomes infeasible, even for relatively small configurations with 4 or 5 states. To deal with this, we apply some specific filters that reduce the number of rules to evaluate. The first one is to reduce the spontaneous life. If we start with an all zeros configuration and a spontaneous activity and an spontaneous activity appears, this is undesirable. To avoid this, the rule must be a multiple of k, being k the number of states. In other words, the last position in the rule vector must be 0. If we see in this animation, we start in a null configuration, and all the rules that are testing here are not multiples of k. They have a value in the last vector. That's the reason that it's creating a spontaneous life. The second filter, the opposite, is the spontaneous death. That means that the rules evolve just for 0 steps. If we start from a single active cell of value 1, the neighborhood sum will always be 1. If the corresponding rule assigns a 0 value to the only condition, the pattern never will grow. Therefore, the penultimate position must be different from 0. If we put a 0 on the last position, it never grows. If, on the other hand, we set it to 1, we create some cases of infinite triangle growing because all the neighborhoods sum at the extremes be always 1. And we can see in this animation because all the extreme values are always the same, that in this case is 1. The last filter didn't avoid all the infinite triangle growing. For this filter is necessary to define what is a complete triangle growth, and it's the one that has width of 2 times the number of evolution steps times the radius plus 1. We can define if a rule evolves into a complete triangle if in the subset from -k to -2 of the rule vector, let's call it middle vector, contains at most 1 non-zero value or do not produce infinite triangle growing. To find this infinite triangle growing, it's just necessary to test all the configurations, but just for the middle vector, with all the resting zeros. Here in the left, It shows the evolution with triangle growing and here without. As we can see, it only testing the minus k minus 2 middle vector for both cases, and we are splitting them just for the infinite growing or not. Then we can try it with different configurations in the rest of the rule vector. Obviously, it affects and determines if a rule creates finite life form, but those are acceptable exceptions. By applying these filters, we can make a drastic reduction of the search space or using the next approximation function, where dk is the number of acceptable middle vector rule. These filters allow us to focus on rules that have the potential to produce meaningful finite dynamics. The first approach is a brute force search, where we treat each valid rule as a node in a graph where the neighbor is generated by applying single-digit changes to the rule vector for all the possible states. For this, we start from the root rule, the zero rule, and explore its neighborhood. If a mutated rule produces a finite life form, we connect it in the graph. Using this method, we discover something very interesting, that is, all finite life form producing rules form a connected component. This means that from any valid rule, we can mutate it or weigh step by step toward rules with higher lifetimes. This observation turns the search into an optimization problem. We want to move through this graph toward regions with longer living patterns. For small configurations like K3 and radius 1, the longest lifetime we found was 88, like is showing this plot. And there are some regions, for example, these green dots have the same evolution. Similar results appear for K4 and radius 1. To explore this enormous rule space, we use a genetic algorithm. This algorithm maintains a population of candidate rules and uses biological principles such as selection, crossover, mutation, and replacement. But for this, it's necessary to initialize a random population the size m, where each individual is a rule in the search space. Then we apply the tournament selection to create the parents set. We chose randomly n elements in the population and choose the one with the highest fitness to be part of the parents population, which is the number of steps it takes until vanishing. We need to repeat this until get the same size as the initial population. Once we have the parents, it's necessary to apply a cross. In this case, by applying uniform cross. We took, for each pair of parents, we generate a binary mask that defines the gen or the rule recombination. For example, if the value in the mask is 0, the first child takes the value of the first parent and the second child of the second parent. But if it's 1, the first child takes the information from the second and the second child for the first. Then it's applying a random mutation in individuals' genes just to maintain diversity in the children's population. We choose children randomly and a gene or a position in the rule vector just to change the value. Finally, it's necessary to apply the replacement. We join the initial population and the children population just to sort them by the fitness function, which is who is the largest. Here is an example of the genetic algorithm. At the beginning, we start with a population of 20 elements, 20 solutions in the space, and we start selecting just to create the tournaments. For example, here, we are choosing these 3 solutions, and the one with the highest has trinity. So this one be selected to be part of the parent population. Then we apply the cross. In the cross, we choose randomly two different parents, define a random mask, and create the new two children. The mutation is applying, and finally, we are selecting who will be part of the next population. This process is repeating until reaching the highest evolution possible or a number of iterations. One key insight is that rules with long lifetimes often share specific subsets of digits in the rule vector. These subsets behave like genetic motifs that improve survival. Generation after generation, the population tends to converge toward promising areas in the rule space. However, this becomes harder to compute because we are evolving n or 20 different rules at once. So it's designing this third approach. That is simulated annealing with a Poisson probability distribution. But first, what is simulated annealing? Simulated annealing starts from a single random rule and a high temperature. We look in the neighborhood of this initial solution and compare with the current solution. If it's better, we keep it, but if it's worse, may keep it with some probability that depends on the temperature. Once we choose something, it's necessary to decrease the temperature gradually to exclude random changes and repeat this until the system gets freeze or a stop condition is reached. Here is an example. It starts moving from different points and try to find the best solution. It starts in this point, looking in the neighborhood and move. How it can find best solution, it start moving to worst, but just to find another peak. In this, try to escape for one side and returns to the peak and try to the another side. Once he reach a point and it gets freezing, it's hardly to get out of this peak. Now, we use a dynamical Poisson distribution to assign probabilities to neighbors. Poisson use a lambda value that if lambda is low, all neighbors are equal probable, promoting wide exploration. If we have a high lambda, neighbors with better lifetimes are more likely, promoting local refinement. When a new best rule is found, we temporarily lower lambda just to focus on nearby configurations, then gradually increase it again. And here are some examples. Starting again from the rule 0 in K3 and radius 1, we start moving into the space and applying random changes, accepting the one who is better, but if we cannot find another who is better, we can start selecting the worst conditions. It's necessary to keep accepting this worst condition because to explore the search space. This one is for K4 and radius 1. Here we can see that it gets stuck in some specific configurations for the temperature or the lambda that is working with it. And this one is for K5 and radius 1. As we can see here, it's really hard to move from one peak to another. There is no direct path just to be increasing this algorithm. So simple path algorithms like hill climbing didn't work well because they getting stuck very quick. There are several directions to continue TS research. The first is analyzing configurational relationships. We want to understand how different configurations, states, and radius influence the emergence, stability, and morphology of finite lifeforms. By studying patterns across parameter sweeps, we can detect trends that predict when and where long lifeforms appear. Second, exploring the structure on the fitness landscape. We want to map local basins, ridges, and rotation gradients to understand how difficult it is to evolve long lifeforms. This includes characterizing bottlenecks, ridges, and neutral networks. Finally, designing new evolutionary strategies. Since this is fundamentally an optimization problem, we plan to incorporate more advanced techniques such as novelty search, coevolution, covariance matrix adaptation, etc. This may help discover exotic behavior that traditional methods overlook. Overall, this future work aims to better describe the structure of the rule space and understand why certain regions produce complex behavior. There is still a lot to explore, but these results provide a promising foundation. That is all for my presentation. I want to thank personally Stephen Wolfram, Stephanie Bauer, and especially William Nielsen to make possible this project. Thank you very much for your attention.